Nope, everybody's happy. Okay, so just so for recording purposes, what we were doing here is we were looking at the first problem. The limit is x approach 5 from the right of this particular rational function. I did a substitution with a 5. I got 8 over 0, the 0 in the denominator with a regular value in the numerator, or like I have written in the notes, not a 0 over a 0, tells us that we have a vertical asymptote at x equals 5. Okay. If we are presented with a function graphically, okay, this is just kind of a little side note, you know, vertical asymptotes are easy to spot. You know, we'll see a graph, we'll see some kind of vertical line. Oftentimes I meant for it to be dotted. It'll be like that. Okay, and we might see a branch of function on both sides doing something like that. And let's pretend for a minute that this is at x equals 3. I would say that the limit as x approaches 3 from the right on this particular function graph yields not in fact a limit, but a behavior of approaching negative infinity. Whereas if I was looking at the limit as x approaches 3 from the left, of the function, I would say positive infinity. So if I take my little pen guy here and I trace, here I am, I'm to the right of 3. Remember that this guy is, he's the right side. So the right side of 3. So on the graph, to the right side of x equals 3, going towards x equals 3 has me going down, 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 versus the left side of x equals 3 heading towards x equals 3 has me going up, 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 up. So with a graphical presentation, when we're looking at a graph, it's easy to see exactly what's happening vertical asymptote wise. The vertical asymptote's there, big dotted line, graph running towards it, and then going in one of two directions. Without a graph, the question is, well, how can I know what is the behavior as x gets close to 5 from the right? Now, could we make a graph? Sure. We've got the ability to do that easily with multiple types of technology. We have graphing calculators that'll do it. We've got Desmos that'll do it on our laptop. We've got the Desmo app that'll do it on our phone. We can graph a rational function like that and see what's happening. What I want to make sure that you understand, though, is if we could not do that, if we could not magically pull the graph and look at it, we could still determine what's happening. We can still decide and figure out numerically whether I'm doing this kind of thing, heading towards the asymptote and heading down, or to negative infinity, or heading towards the asymptote and heading up. Okay. So let me show you how we're going to do that. If I go back to my problem here. Now, once again, just a quick review, I want to know what's happening as I approach 5 from the right. So 5 from the right means, let's go here, okay. X gets close to the right, to 5 from the right. That means we're coming in from numbers greater than 5. So like 6 and 7 and 8 and 9 and 10, but driving towards a 5. So I'm going to do exactly that then. If I want to know what's happening, let me zoom this down one more notch. There we go. If I want to know what's happening as I get close to 5, but I'm coming in from numbers bigger than 5, I'm going to make myself a table. And I'm going to go bigger than 5, but I'm going to start getting close to 5. So maybe I'll do an 8, a 7, and a 6. That way I'm getting close to 5. I'm coming towards 5, but I'm not at 5. And if you really want to do something fun, you want to throw a decimal in there, we could go to 5.5. So we're coming in from numbers bigger than 5 towards 5, and we're going to see what this function is doing. Either my f of x's are going to get, my y's are going to get bigger, or they're going to get smaller. Now, this part's a lot of crunching of numbers. 8 plus 3 divided by 8 minus 5 is 11 over 3, which is like 3.6 repeating. It's 3 2/3. It's almost 4. That in itself doesn't tell us anything. What's going to tell us what's going on, or at least start indicating what's going on, is how the second number now, as I go from an 8 to a 7, what happens to my y. So 7 plus 3 over 7 minus 5 is 10 over 2, which is 5. Okay. So if I were going to bet what this graph looks like as x approaches 5 from the right, I would bet going to positive infinity, because I took a step closer to 5 and my y got bigger. Let's convince ourselves a little bit more. 9 over 1. There's one more step towards 5. And it got bigger, and it got bigger by a greater amount. Like from 3.6 to 5 is less than 2, but from 5 to 9 is 4. So the growth from here to here, and then the growth from here to here is growing. If you want to do one more, if you are not afraid of the decimal, the 8.5 divided by 0.5, which is basically 8.5 times 2, exactly. That's 100% right. Dividing by so write that down again. So 8.5 divided by a half essentially is 8.5 times the reciprocal of a half, which is 2. And so look, we've jumped not quite 2, and then we jumped 4, and now we've jumped 8. And we've jumped 8 with only a 0.5 difference. Here it was a 1. 1 smaller made us 4 bigger. Here, a half smaller made us 8 bigger. The growth is clearly showing that this guy, oops, the limit as x approaches 5 on the right of that is going to be positive infinity. Now, let's get real for a second. When I have a function that's relatively easy to graph, and I've got a tool to graph it, it's very easy to generate that exact same result. Okay. it doesn't take much of anything to graph that function, to look at the asymptote, to see that you have the asymptote at 5, and then to verify exactly what we just did, which was, you know, I plug in an 8, and I get like 3.6-ish. It's hard to get to that 8. There we go. And then I go to 7. And so basically, I don't have to look at it if I just look at individual points here. As I go closer to 5, but coming from numbers bigger than 5, I can see my y's are growing. And it's getting steeper and steeper. The amount of change from, you know, the change in y compared to the change in x is also growing. I mean, here I'm getting very, very small intervals of change. But my y's are getting big, and I can to the point where it almost is ridiculously straight, right? And the calculator can't, and the Desmos can't really keep up with it very well. Without the ability to generate a graph easily, this is where we are. Looking at some numbers, estimating, and looking at the pattern. Yes?
Are we allowed to use Desmos?
Yes. You are allowed to use your Desmos, sure. So, if you're thinking like, so, you know, do I have to know this? Yeah, you still do, because if I ask you some questions, when I ask you some questions, you know, about, you know, what does this table, if I gave you a table of values about a function and I said, here's the table of values, what is this showing? Right? If I say I've got an asymptote, a vertical asymptote at 5, and this is what happens as I get close to 5, what are we doing at that vertical asymptote? Right? Well, we must be getting larger. Okay? We must be going to positive infinity. Now, I did say we were going to back up off of a couple of the things I had here. I have several other examples to, oh, I don't have them on here. There are several other examples you can look at to kind of practice this. We've got the one right next to it where you're approaching 1 from the left. You've got one with a 2 squared. You've got one with a square. Let's go ahead and talk about the one with the square real quickly. Okay. So there's the one that looks like this. Approaches 3. In this case, it's from the left. And it's x over 3 minus x squared. Okay. Substitution gives me that. So I know I have a vertical asymptote at x equals 3. We're specifically being asked for left side behavior. So, okay. I'm going to make a table to illustrate this left side behavior. So left side of 3 is, that means we got to start less than 3. So maybe 0 and 1 and 2, and then if we want to throw a decimal in, 2.5. So less than 3 and go up till we get close, as we're getting close to 3. So this would be 0, 3 minus 0 all squared. So a 0 on top is a 0. 1 over 3 minus 1 all squared. So that would be 1 over 2 squared, or a fourth. Two over 3 minus 2 squared is 2 over 1, which is a 2. So 0 to a fourth to 2, what would you say this limit is? Positive infinity, yeah. It's probably positive infinity. The interesting thing about this particular function and what happens when you get that squared kind of thing in the denominator, 3 minus x, quantities squared, there we go. There's the asymptote at 3, and the growth is pretty slow here. You got to get really close to 3 to start getting the, oh, we're coming from the, sorry, I lied. We're coming from the left side. Okay. So we got to get close to 3. So the 0, there's the 0, 0. There's the 1, 1/4 or 0.25. Here's the 2. And then if we can get in and get the 2.5, if we could do that, we're going to see the numbers are going to start to get a lot larger. You need pretty much this kind of denominator where you've got the a double root kind of denominator, something squared, to get it to do the same thing on both sides. Otherwise, 9 times out of 10, it's going to do, we're going to get one side doing one thing and one side doing the other. Okay. So, absolutely can support what's happening numerically. And I will ask for that. I will ask to see some numeric support. You know, show me a table of values that supports that this limit is positive infinity. Now, the part that I decided I wasn't going to have us do without a graph is what's at the bottom. When I ask you in general to do something like this, okay? And this is under, I'm not asking you for one side. I'm just asking you kind of in general. So in general, we know there's a vertical asymptote at x equals 2. But in order to answer the limit question, we got to check both sides. It doesn't say 2 on the right or 2 on the left. It just says 2. So you got to talk to me about both sides. And if the two sides don't match, then we're going to say D and E. So essentially on this kind, I'm not going to ask you for the numeric support because you'd have to do 2 tables, and it's just I mean, I don't even want to do it. And I'm the math teacher, so I can't imagine that you're gonna like it makes me want to roll my eyes. You know, how do I know this is gonna be and I know this is probably gonna be a D&E? Well, because I know if it's like this, typically we see it doing things on both sides. Okay. Oftentimes, just being close to 2, looking at like what the fact that like what a 1.5 would do versus a 2.5. Yeah, I don't like that. No, that's not. I mean, one will be positive and one will be negative. When we've got the tool, we use the tool. All right. This is where I have conflict with myself. Whoops. It's like, if we're in an AP classroom, I'm doing all kinds of crazy stuff. If we're in an AP classroom, we've got to be doing certain things. I'm not deleting, that's the problem. Versus if we're in, and even if you were looking at this at a calculus class at a college level, chances are you'd have access, you may not have access to Desmos, but you'd have access to a graphing calculator. So you could look at the calculator, you could graph it, or you could put it in and look at the table and see, oh, look, it's getting bigger and bigger and bigger on the right side of 2. It's getting smaller and smaller and smaller on the left side of 2. So that tells me that the limit as x approaches 2 of this particular function does not exist. Because we got sort of a positive infinity stuff on one side and negative infinity. Oops, it's an 8. Negative infinity stuff on the other. Okay. Yeah, I've definitely decided in my head I need to kind of rethink about how I talk about this in applied. So this is a little awkward today, but it's okay. I'm okay with what we just did. What you're going to end up doing for me is essentially practicing this with a couple problems that are on that limit worksheet. I believe the 4 problems on there are all asking about one-sided limits. And so absolutely feel comfortable using a graph to verify, but as much as you don't want to do it, see if you can't show me also a table like I did. Make me a little table of a few values that illustrates the pattern of behavior. Okay, I'm gonna stop this. So